Hey guys, so for context, I got an empty classroom in front of me. I'm going to try to repeat what we did in class, but we had some technical difficulties and recording exactly. So here, all right, so first I gave you guys a recap of some things you guys saw on Friday. Not everybody was here Friday, and you guys probably could use a recap anyway. And then we got into some new stuff, doing some calculations with you guys. So looking at temperature, so thermodynamics, heat transfer, how do you measure temperature? What is temperature? So down at the molecular level, you can have atoms vibrating. The faster they vibrate, right, the hotter you would perceive that to be, like the higher the temperature. Right? And so that's called kinetic energy theory of temperature. Now, starting from the Celsius scale here, you guys know that water will either freeze or melt at the 0 degree mark, and it could boil at 100 degrees Celsius. Now, really, that's only true at sea level, right? And that might change in the next day or two. We'll say, hey, what if you go up in the mountains? But we'll hold that for a different day. Right? Now, that's Celsius. That's Celsius, right? But okay, and if you want to transfer to Fahrenheit, you guys know the freezing melting point of water is 32 degrees and boiling could be 212 degrees. Okay? Now, how do you translate from Fahrenheit to Celsius or Celsius to Fahrenheit? Here's Celsius to Fahrenheit right here. Okay? Okay, so if you're in a foreign country and you say the temperature is something, you say, okay, times 9 fifths plus 32, and I can get like American units like Fahrenheit. Okay? Okay, but the problem with both of these scales is that they're relative scales. So if you wanted to apply temperature to an equation, like for example, ideal gas law, notice this doesn't say, so I got pressure of the balloon, volume of the balloon. Notice this T doesn't just say temperature, it says absolute temperature. So for example, if I hold a candle up to this balloon and heat it up, I think it should expand. If this T doubles, I think this V volume should also double, for some given pressure and everything else equal, right? Right. But what is doubling temperature? Now, if you're working in relative scales, it doesn't make sense to talk about temperature scaling up by some factor because these can go negative. What you need is an absolute scale. You guys see this Kelvin scale over here starts at 0, and the 0 is called absolute 0. So that also corresponds to these temperatures in Celsius and Fahrenheit. Right? So there is a lowest temperature in nature. Like you cannot go below a certain temperature, right? Where everything just kind of starts vibrating. You think of it that way. Right? And you have to use the Kelvin scale in these equations. So here, I'll do a numerical example like I did in class. I say, suppose you heat a balloon from, let's say, let's go 10 degrees Celsius to 20 degrees Celsius. Okay? So I'll give you guys a visual right here. So here's a balloon. I'm going to hold a candle up to this balloon. Okay? And because I'm heating it up, it will expand. So it's going to get bigger. Call this V1 and call this V2. So volume 1 and volume 2. Okay? So how much does the volume expand as a result? And we'll do a proportional answer. Right? So the could be 1 cubic meter or whatever the volume is. It's going to expand by some proportion. Okay. Now, if you take the numbers at face value, you say, oh, well, let's say 20 is double of 10. Right? But you have to be careful because the temperature is not doubling, not the absolute temperature. Okay. So we got to figure out absolute. So we got to translate the numbers over to Kelvin. And that is this one right here. Temperature in Kelvin is temperature in Celsius plus 273. Let's just chop off the 0.15. Don't worry about that so much, but plus 273 is going to be the conversion. So let's do that. Okay. So I'm going to say the absolute temperature initial, right, like the first temperature was 10 degrees Celsius plus 273 is actually 283 Kelvin. Okay, that's what I want the Kelvin. Okay. And the new temperature is going to be at 20 degrees Celsius plus 273 is actually 293. And that's Kelvin. Okay. Now go to this ideal gas law right here. Right. I'm going to write this down. We'll do the old and the new situation. I'll say pressure volume 1 equals number of moles of gas, constant, and then absolute temperature 1. And then we'll go, I'll write the second equation above it. So I'll set up the fraction better. Pressure volume 2 equals nRT2. Okay. So these are different volumes and different temperatures, but they are the same pressure and the same everything else. So if I divide these equations, okay, divide this by this, okay, then a lot of stuff cancels. I can get the ratio of volumes, which is really the question, how much does the volume expand proportionally? Right? Okay, so we're set up to solve here, is really the ratio of the temperatures. Okay. And again, I'm not allowed to do 20 over 10. No, because those are relative values in Celsius. I have to do these absolute temperatures in Kelvin. So let's go to 293. over 283. So Kelvin over Kelvin. Now this will tell me the correct proportion. And what does that turn out to be? 293 over 283. That's 1.035 something something. I'll just chalk it off there. Okay. So what I can say is that the volume expanded by 3.5%. That's one way to say it, because it was 1 unit of the volume, now it's 1.035 units volume. So it got bigger by 3.5%. Right, what is it? All right, so we did a tie in here. Okay, so absolute temperature scale is useful to ideal gas law. Okay, we got that. We got these temperature conversions, formulas. Okay, we applied this. Okay. All right, laws of thermo. Okay, so went over these on Friday. So quick recap here. I'm gonna focus on these. And really the first law of thermo is one that you know already. It's basically conservation of energy. We just have a new energy unit, or sorry, a new energy formula, which is thermal energy, thermal energy. And thermal energy, here's a good formula for it. Right. Delta Q is like a transfer of thermal energy. So when you see Q this week, capital Q, we're talking about thermal energy, it's MC delta T. So the mass of what you're working with, specific heat capacity, and like some change in temperature correspondence. Right? It's kind of analogous to like MGH was potential energy last semester. Right now we have thermal energy is MC delta T. You think of it that way. Right? But anyway, whatever energy is lost by one object is picked up by another. You cannot create or destroy energy. You guys have known that since last semester. Now, what we really have to expand your imagination is the second law of thermodynamics. This is the one that says, as time moves forward, processes tend toward less usable entropy and more disorder, and entropy in the universe always increases, right? Like overall. So why do processes happen one way but not another, right? Why is it that if I mix, say if I stir sugar into coffee, I can't unstir it out, right? Once it's mixed, right? Or why can you take a like high quality energy, like the energy in a gallon of gasoline, you run the car, but then once you've expended the energy doesn't disappear from the universe, but it is less useful, right? You can't get that energy back and make the car run more, right? So what's with these processes, right? Right now there's a let's talk about this entropy, right? It's linked to like certain time order processes. So hold on to that idea, right? Now this is kind of an analogy, right? Like if you look down at molecular level, you can think it's like molecules being like grains of sand. Okay? So what if you have a highly ordered sand castle and you leave it there on the beach and come back a few hours later, and now it's a random pile of sand, right? And one way to think of this is that statistically, and the second law of thermo really is a statistical outcome of the universe, right? Is that there are more ways for the sand grains to be arranged to be a random pile of sand than it is for a highly ordered sand castle. Okay? So I would expect spontaneously for the left picture to turn to the right picture, but never the reverse. I can't just make a random pile of sand, come back, and the wind just randomly blown it into a highly ordered sand castle. It's not going to happen. Okay? And a change in entropy, that's what this is. So entropy is S, is the thermal energy that's transferred. You guys saw that. Okay. Delta Q. Divided by the absolute temperature of the Savin side. And as a rule, second law, this is the second law of thermo on the bottom right side. The change in entropy as time moves forward, so change in entropy or change of time always increases. That's what this says right here. Okay. So let me throw these terms down. So delta Q is transfer of thermal energy. Okay. When we see delta S, that's a change in entropy. Right? You can think of it like a increase in disorder or a decrease in availability of useful energy. Right? Okay, so let's look at another entropy example. This maybe makes more sense. Okay, so here's the same formula you guys just saw. Right? Copy paste it over here. So the change in entropy for one of these blocks we're about to look at, or this is the universe as a whole, is the transfer of thermal energy divided by the absolute temperature this happens at. Let's say you put a hot block next to a cold block. So we've got a 30-degree block next to a 10-degree block. Now, if those were, say, isolated system, suppose it's like in a styrofoam container, and you walk away and come back a few hours later, I would fully expect these to reach equilibrium eventually. And now they're both 20 degrees. Let's say the same materials, same mass. One was hot, one was cold. Now they're the same temperature, right? And you would expect this to spontaneously turn from the top picture to the bottom picture, but never the reverse. You're never going to put a 20 degree next to a 20 degree and come back later and one's randomly picked up heat energy, like thermal energy from the other one. That's never going to happen, right? But it always goes from the top picture to the bottom picture. So let's throw in another number here. Let's say that, based on the masses of these and whatnot, say we end up getting 100 kilojoules of energy transfer. Okay, so let's run this entropy uh, expression right here. Remember, S is entropy. I just showed you guys that. Okay, delta S is changing in entropy. Okay, so we have 100 kilojoules is being lost by the hot block. So we're starting with the hot block right here, the hot block cooling. Okay? So this is losing thermal energy. That's why I put a negative right here. Okay. Divided by the absolute temperature it happens at. Now here's where we're going to fudge the math a little bit, but that's okay. It'll be close enough to work. I say, well, what's the average temperature going from 30 degrees to 20 degrees? Well, that's at 25 degrees. So that's where the 25 comes from. But remember, I can't just use the Celsius value. I have to use the absolute value. So I'm going to say plus 273. Okay. And here's the change in entropy for the hot block cooling. Now this one actually loses entropy during this process. That's interesting. Hold on to that. So we got a negative number. Now let's look at the cold block heating up. Well, the cold block heating up gained that thermal energy. That's why this value is not positive in the numerator. It's the same with the numerator otherwise, just positive. Okay. And what's the sort of average value of it going from a cold value to the lukewarm value? Okay. So from halfway between 10 and 20 degrees is 15 degrees. Now that's Celsius. I'll say plus 273 to make this Kelvin. Now I have an absolute temperature. Okay. And you run the numbers, and now the cold block warming up has gained 347 joules per Kelvin, like units of entropy. Now, what's the change in entropy for the entire universe? Well, all you have to do is tag these two parts together. You say, well, the hot block cooling down lost entropy. That's this right here. The cold block warming up gained this entropy. That's right here. And altogether, there's a net change that's always, always, always positive. That is what the second law of thermo says. I go back to, but where's my laws of, here's my laws of thermo. Okay. See where it says entropy always increases in the universe, Okay. So from a universal point of view, yeah, again, we got individual block, but the two block system is what I'm considering the universe in this case. Yeah. So always here. So it's how fractions work, it's how statistics work. Okay. That's what the second law says. Okay. All right, we talked about forms of heat transfer. Conduction is direct contact. Convection is you got fluids mixed with bulk movement of fluids. This is hot, this is cold, it wants to mix. And then radiation is the electromagnetic waves. And you guys told me in class, you said, oh yeah, that's the only one that can travel through the vacuum space. That's how sunlight reaches Earth, is radiation, right? Electromagnetic radiation. Right? I think we looked at this on Friday officially. Right? So you put a gallon of gasoline in your car, right? It makes the car go. That's useful work, right? But also the engine gets hot and it heats up. Also, your car's plowing through a bunch of air friction, right? Those are like waste heat, right? Not really making a car go, right? So what's the efficiency? Is the useful work divided by the energy you put in, say in the form of gasoline, right? Your car engine is probably approximately 30% efficient. Right? All right, this one right here. So I'm telling you guys, I think I mentioned before, I'm not going to be at school on Thursday. I have a jury summons. But I am pulling together a packet for you guys that has a lot of thermodynamic questions, and I'll have you guys work in teams so you guys can help each other out. But one of the questions is going to involve this heat curve right here. So let's go through this heat curve. Okay. I'll do a numerical example with you guys and see some very similar questions on Thursday. So vertical axis, I got temperature. Horizontal axis, I got a transfer of thermal energy, which is called heat. Right, so heat energy. Okay? And the scenario here for water, it got different phases of water. Okay, so we got like an ice cube, we got liquid water, we got steam. It's all in this graph, and I'll show you guys how. So you guys see the general trend is up and to the right. So what I'm going to do is I'm going to take a block of ice. Ooh, a block of ice, that could be less than 0 degrees Celsius. So I pull that straight out of the freezer. I'm going to put that on the stove and let it heat up. Right? And it's going to go through the process. Now, guys, as it's gaining heat energy from the stove, I'm talking about the block of ice. The block of ice is gaining heat energy from surroundings. Okay? That would be going to the right, and its temperature as a result will be going up. So overall, this goes up and to the right. But not exactly every single step of the way. I see some exceptions to that. Why is it all jagged like this? Why is it all jagged? So let's go through step by step. So first thing is I pull that block of ice out of the freezer. It's very, very cold. I have to bring it to begin to melt, right? And then when it hits this point right here, 0 degrees Celsius, now it finally starts to melt. Now this entire horizontal leg of the journey, the temperature is stuck at 0 degrees. But it's undergoing a phase change. Over here, it's 100% solid ice. Over here, it's 100% liquid, puddle of water. Right? Now, once it's 100% liquid water, then now you can start to increase the temperature as it's still absorbing heat from the surroundings, say from the stove. You do that. Right? But that phase change, the temperature stuff. If you have a glass of ice water, suppose you have a glass of ice water, you can imagine that. Right? Maybe it's been sitting there for about an hour, got temperature equilibrium. Right? I can tell you what that temperature is. It's exactly 0 degrees Celsius. It's somewhere on this horizontal part. Right? So if it was 100% block of ice, maybe it'd be like on this side. If it's 100% water, the last dregs of ice melt would be over here. If it's a mix, like 50-50 mix, it's probably right in the middle, right? So it's gaining heat energy going to the right. And when it's allowed to move up on the graph, that'd be increasing temperature. Okay? Right now, we're going to take that puddle of water and we're going to heat it up, heat it up, heat it up until finally it starts to boil. And here's another phase change called evaporation. Over here was melting, now we got evaporating. Right, so here's 100 degrees Celsius and it begins to boil, and then boil, 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 and then here's 100, still 100 degrees Celsius, but now it's steam, right? Now notice that entire process of boiling, it's the temperature is stuck at 100 degrees Celsius. If the water starts to boil and you turn up the flame on your stove, it doesn't actually make the water any hotter at all. Well, no, it'll boil it away faster, right? But it doesn't actually raise the temperature. You can't raise the temperature until it all turns to steam, and then the temperature is allowed to increase after that, right? This is given some pressure, say like sea level pressure. So let's run an example here. So we'll do this example. So let's say I have well, you know what, in class I had a 1 kilogram block of ice. I'm going to change that to make it a little spicier here. What if I have let's say a 2.4 kilogram block of ice? Let's do that, block of ice. Okay. Let's say at -5 degrees from freezer. Right, so there's a scenario. Got this 2.4 kilogram block of ice. Okay, get that out of the freezer. Yeah, it's at -5 degrees Celsius. I'm going to put this on the stove, okay, and I want to know how much energy to boil it away into steam. Okay, now to boil it into steam, really we got a multi-part process because this block of ice we got to bring it up to begin to melt. Okay, so here, let's do the roadmap. Let's look at this picture right here. Right? We got to bring it up to begin to melt. Then the whole thing has to melt. Then we got to bring it up to begin to boil. Then we have to boil it all the way. That's going to be a 4-part process. And so here, I'll spell that out. So we got like one of the journey is bring, so I'll call it part 1. Right? Bring ice to begin to melt. Right? That's this part of the journey right here. Right? Part 2 is melt all the ice. Okay? That's going from here to here. That's this horizontal part. Part 3 of the journey is going to be bring the now liquid puddle of water to boil. Okay? So that's going from here to here. Okay? And the 4th part of the journey, part 4, is going to be boil all the water away. Right? Boil all water into steam. Okay. And let's end the journey right here. Right? When the last liquid water finally turns into steam, we'll stop the journey right at that coordinate. Okay. And so how do you create equations for these? And actually, the only 2 equations you need are right here and right here. So we're going to solve this 4-part journey with these 2 equations. All right. I'll show you guys how. So first thing first here. All right. So I'll call this part 1. Right. So you guys know what that corresponds to. Right. Bring the ice to begin to melt. So I'm going to say the transfer of energy is equal to mc of ice, I should say, delta T. Okay. So here's transfer of energy, which is what we're solving for, like how far horizontally do you move on this graph. Okay. We're going to take 2.4 kilograms of ice. Okay. Now, this C is the specific heat capacity of ice, okay, which I got right here. It's 2.09 kilojoules per kilogram Kelvin. It's right there. Okay. So right here goes 2.09 kilojoule. Well, guys, actually, you know what, guys, when I'm talking about kilojoules, you guys know kilos 1,000, right? I may as well just go times 1,000. Let's just do joules per kilogram Kelvin. So everything's in base SI units. I should really do that. Let's do it. And then changing temperature. Well, guys, if we're going from -5 degrees up to 0 degrees to get it to begin to melt, you guys see this delta T is basically going to be 5 degrees. Okay. Now, change in temperature of 5 degrees Celsius is a change of 5 Kelvin. Okay. And I can point that out right here. These are scaled the same, they're just shifted. Right. Here's another picture. Okay. You guys see that going from 0 to 100 degrees Celsius, going from 273 to 373 Kelvin? The change is the same, right? They're both 100 temperature units either way. Okay. So it's okay to put in Celsius if it's a temperature change. It's okay to use Celsius in the equation because this could also be 5 Kelvin. It's the same thing. All right, so let's try this. Let's go to 2.4 times 2090 times 5. Okay. And this works out to 25,080. Well, it would be joules, wouldn't it? Because the Kelvin cancel, kilogram cancel. Okay. So now we know how much energy during that first leg of the journey, just to bring the ice to begin to melt. And it's just this little bit right here. Okay. Part two. Okay. Now we got to, and I spelled it out right here, melt all the ice. So that's this leg of the journey right here. Okay. Now it's a little bit different looking formula. You guys see this delta Q is M delta H. Okay. So this is for a phase change. I'm going to do M delta H. Now this is delta H at fusion, which is the ice melting. So I'm going to do 2.4 kilograms of ice. Okay. And the delta H for ice, actually it's right here. It's 334. Okay. And what's the units on that? Well, okay, also kilojoules per kilogram Kelvin. So I'm going to say times 1,000 to make it joules per kilogram Kelvin. Yeah, got rid of the kilo. And so what's this number? What's 2.4 times 334,000? I'm looking at 801,600 joules. Okay, so a lot more energy. Okay, it's many times more energy to get all the ice to melt. Okay, now we got a puddle of water. Where are we going to do that puddle of water? We have to go from this point on this curve to this point on this curve, which is we're going to bring it to begin to boil. So that's part 3. So let's move on to part 3 here. Part 3 of this journey, bring the water to boil. So we're going to use this equation right here. So delta Q, the thermal energy transfer, is mass of water times specific heat capacity of water times the change in temperature of water. Okay. Now we still got the full 2.4 kilograms. We're still working the same mass. Okay. Now what is the specific heat capacity of water? So this is a number you see all over in different science classes. It's this number right here, 4184 joules per kilogram Kelvin. Looks like, okay, this one I did leave in joules, so let's go to that. Okay. So this is 4184 joules per kilogram Kelvin. Okay, and the change in temperature, well, guys, we're going from 0 to 100. The change is 100, and that could be degrees Celsius, but that's also Kelvin because it's the same temperature change. Okay, so let's get a number for this. 2.4 plus 4184, where's the not plus? It's times. Okay, times 100. Okay, the Kelvin cancels, kilogram cancel. This is 1 million joules. So, so it takes that much energy to bring the water to begin to boil. And actually, just look at this heat curve because I tried to make this pretty well to scale as far as I could. Right? It looks like we had a little bit here, then like a medium here, again some here. Okay? Looks like probably the vast majority of energy is going to get it to boil into steam. Because we're saying another way to answer this question is like how far do we move horizontally on this graph? Okay? So we got to boil all the way from this point here to this point here. And that's a huge jump right there. So part 4 is probably going to be the vast majority of the energy anyway. So we're back to delta Q equals M delta H. Okay. Now this is the heat of vaporization. It's kind of like the formula we did before for melting, but now it's to boiling. Okay. So we still got the same 2.4 kilograms that we've had all along. Okay. But what is the heat of vaporization for water? I got it right here. It's 2265 kilojoule per kilogram. Okay, now we're back to kilo. So 2265, but I'll go ahead and multiply by 1,000 for that kilo right there. 1,000, that's joules per kilogram Kelvin. Okay. That's 2.4 times 2,265,000. Okay, and that is 5 million something joules. Yeah, definitely the biggest number we've had so far on this 4-part journey, okay, which also aligns with this picture. Okay, so let's put it all together. Right, there's parts 3 and 4. Right here, here's the initial question. Right, parts 3 and 4. Okay, and then here's parts 1 and 2. Okay, and I circled all the energy values associated with all 4 parts. So now all we have to do is add these together. Here, I'll just go ahead and add these together on my calculator screen. Okay, part one, part two, part three, part four. Okay, let's add it all together. So I'll say that sum total energy is 25,080 plus 801,600 plus, and then over here, 1,004,160 plus, and then 5,436,000. Okay, so the sum total energy, or maybe I should say like delta Q, think of it that way, is I got 7,266,840, and that's joules. There you go. And that's the final answer to that initial question of, let me go back to the initial question. Remember this, how much energy does it take to boil this ice cube all the way on into steam? Yeah, there we go. Like 7 point something million joules. All right, so 4-part journey. One thing I'd say to be careful about is some of these values are listed in kilojoule per kilogram, and like this one right here, went ahead and left in joules rather than kilojoules. Anytime you see kilo, go ahead and multiply by 1,000. Okay, we had to use some of those numbers. Yeah, okay, and then the bell was about ringing, so there's a little bit more to this adventure continues, but we'll have to say future adventure for tomorrow.